For 50 years, a fundamental limit in computer science stood completely unchallenged. It was like a wall that defined the relationship between how long a program runs and how much memory it needs. Well, today, we're explaining the breakthrough that just smashed right through it, a brand new way to simulate time with just the square root of the space.
You know, it all boils down to a question that sounds almost philosophical, but it's actually at the very core of all computing. How does the time a task takes relate to the memory or space it needs to do it? And this isn't just some academic thought experiment. It's the heart of a massive unsolved mystery known as P versus P space, a problem so tough and so important that solving it is basically one of the holy grails of theoretical computer science. So, to really appreciate why this new breakthrough is such a game changer, we first need to get a handle on the two sides of this epic challenge.
Okay, so on one side, you've got P, which stands for problems that can be solved in polynomial time. All that really means is they're relatively fast. If you double the size of the input, the time it takes might quadruple, but it's not going to explode into billions of years. On the other side, you've got PS space for problems that can be solved with a polynomial amount of memory or space. The easiest way to think about it is this. Time is how many steps you have to walk. Space is the size of the notepad you're allowed to use. Now, we know any problem that's fast can be solved with a decent-sized notepad. The real question is, are there problems you can solve with a tiny notepad that just have to take an impossibly long time to walk through? And here's the thing. The consensus among experts, including Ryan Williams, the author of this paper, is that P and P space are not the same. They believe that yes, some problems are fundamentally easy on memory but incredibly hard on time. The problem? For decades, nobody could make any real progress on actually proving it. And that lack of progress meant that for a very, very long time, scientists were just stuck at a specific wall, an old limit that defined the best we thought we could ever do. Yeah, you heard that right. For half a century, the best-known trade-off between time and space in these theoretical computations just went completely unchallenged. This was the line in the sand nobody could cross. For 50 years. So what exactly was this old limit? Well, way back in 1975, a trio of computer scientists, Hopcroft, Paul, and Valiant, set the record. Their formula basically said that the amount of memory you needed was pretty much tied directly to the runtime. To save a little bit of space, you had to pay a small price in time. And for 50 years, that was it. Everyone thought that was the best trade-off you could get. And that brings us to this new paper, which pulls off something that, frankly, many in the field thought was impossible. It introduces a completely new kind of simulation that just shatters that old trade-off. I mean, just look at this comparison. The old method needed an amount of space that was roughly proportional to the time t. The new method? It only needs space proportional to the square root of the time. To put that in perspective, if your time t is 1,000,000 steps, the square root is only 1,000. This is a monumental leap in efficiency. It's like going from needing an entire library to needing just a single bookshelf. And this chart just makes it crystal clear. The reduction is dramatic. If the old method needed a huge chunk of memory to run, this new method gets the exact same job done with just a tiny fraction of it. This isn't just a small tweak, it's a fundamental change in how efficiently this can be done. Okay, so how on earth is such a massive improvement even possible? Well, the secret sauce is this really clever technique called tree evaluation. So, instead of thinking of a computation as one long single file line of steps, this new approach completely reframes it as a tree, kind of like a family tree. The final answer you want is the root at the top. But to figure out that root, you only need to know the answers from the branches directly below it, its children. You can then pretty much forget about the root and just focus on figuring out one of the children. What this means is you never have to hold the entire history of the computation in memory all at once. You just need to remember the specific path you're currently on. So here's how it works. First, the whole timeline of the computation is chopped up into smaller blocks. Next, you map out how information from an early block might influence a later one. Then you take this map of dependencies and you structure it as that tree we were just talking about. And finally, and this is the absolute key, a hyper-efficient algorithm navigates this tree to find the final answer, calculating only what it needs for the current step and then tossing it. That's how it saves an incredible amount of space. And you know, a breakthrough like this doesn't just happen in a vacuum. It was only made possible because of another very recent paper from Cook and Mertz. They're the ones who developed the amazingly efficient algorithm for tree evaluation that this whole new simulation is built on top of. So what does this all actually mean for that huge question we started with? How does this new, incredibly efficient simulation help us understand the gap between fast problems and low memory problems?
Well, it has some major implications. For the first time, it actually proves that some problems that use very little memory must take a long time to solve. We're talking if a problem size is n, the time it takes will be close to n squared. It also gives us more efficient tools for really complex tasks, like verifying the design of a computer chip. But really what it does is forge a much stronger, clearer link between the time a computer spends and the memory it needs.
Now, let's be really clear. This doesn't solve the entire P versus P space problem. The author himself calls it a little progress. But in a field that's been stuck on this for half a century, a little progress is a massive deal. It's the first real, provable step forward in decades. This new way of thinking, transforming a line of time into a space-efficient tree, is a radical shift. It leaves us with a tantalizing question. Could this new approach, this key that just unlocked a 50-year-old door, be the one that finally solves one of computer science's greatest and most profound mysteries?